Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 5.2, Atomic Operations. The purpose of this lecture is help you to understand atomic operations. And especially, we're going to introduce the concept of read, modify, write in parallel computation. And then we're going to also explain the nature of race conditions when performing read, modify, write, which is a major problem in parallel computation that lead to bugs and errors. Here is a common collaboration pattern. When we have many people work together, for example, in a situation where we have many bank tellers count the total amount of cash in the safe. And a good way to collaborate is for each teller to grab a pile of cash and count. And then after finishing a pile, the teller will go and update a current sum to incorporate the amount of money in the pile that he or she just counted. And whenever this happens, we have a read, modify, write operation where the teller will read the original total and add the total from the pile and then write the sum back into the total. So we're going to have multiple people doing this kind of read, modify, write into that total. And the bad outcome that can come out of it is that some of the piles may not be accounted for. If something happens and the amount of money from several piles were missing, then we have an incorrect accounting process. Another common parallel coordination pattern is that let's say we have a customer service shop, like a cell phone company or some kind of customer service for some kind of merchandise. You have customers coming into your shop, and we have multiple customer service agents serving customers, and each customer will get a number. And there's a central display that shows the number of the next customer who will be served. So when the agent becomes available, he or she will call the number, and he or she will add 1 to the display so that the next agent will be able to serve the next number. And a bad outcome of this kind of coordination is that if for some reason, when multiple customers get into the shop, somehow they all got the same number. And so when the customer service agent announce a number, multiple customers come and say, I have this number, then you have a conflict. People are not going to be happy about that. Or in some case, another situation where multiple agents may serve the same number. When multiple of these customer service agents finish their work, for some reason they all call the same number, then it would look pretty silly. So that's why this is also a bad outcome. Another common pattern of collaboration, coordination, or arbitration is that you can have a situation where multiple customers are trying to book airline tickets. And whenever they finish booking that airline ticket, they're going to reserve a seat, and it will bring up a flight seat map, and the person will decide on a seat and update this and check that seat, and then update the seat map. So hopefully that seat will be reserved for this person. A bad outcome is when many customers are all booking their airline tickets. For some reason, they all end up booking the same seat. And when they all board the plane, they're going to all have a ticket that shows that they have they all are supposed to sit in the same seat, and only one of them will win. And this is actually a frequently happen bad situation in the airline. And when I travel, I often see 2 people ended up in the same seat, and it's not a very happy situation. So all these things have to do with multiple people all trying to update some kind of record. And if some update happen to be lost, then you will end up having a conflict where multiple people may end up getting contending for the same seat, same service, or some of the money that you're supposed to count get lost. So this leads to the concept of atomic operations. If a memory location X is initially 0, and what would the value be for that location if two threads, thread 1 and thread 2, want to update the value, both want to update that value, both want to be able to fetch the original value, add some value to it, and update it. So, and also an important question is, what does each thread get in their old variable value? So the answer can vary due to the timing or data races. In one situation, we could have one thread to arrive earlier than the other thread. So these two threads will each get a different value. And then if the other thread arrives first and the original earlier thread becomes a later thread. So, but that's okay, because in parallel computing, oftentimes we don't really care about the order of these two threads. One can come before the other, and that's okay. But what can be really bad is that when both threads are trying to update value into a variable, the update of one of them gets lost. So this leads to the concept of atomic operations. So here we show the read, modify, write process for each thread. Thread 1 wants to read from the memory location into its register variable old, and then you add 1 to that old value to generate a new value, and then you write that new value into the memory location X. Thread 2 also does the same thing. So now we can analyze some timing scenarios and see if these scenarios are reasonable or not reasonable. The first scenario is thread 1 will perform all its 3 read, modify, write operations before thread 2 does its read, modify, write operations. So in this case, thread 1 will receive an original value 0, and then you would add 1 to it, so you would update the variable to 1. And thread 2 will receive that 1 value, which is updated from thread 1 because it came later, and then you will add 1 to it, it will generate 2, and then you will leave the memory location as value with value 2 after it's done. So thread 1 receives the original value 0, and thread 2 receives an original value 1. And this is a perfectly reasonable result, and the memory location has a value 2, which reflects both the updates of thread 1 and thread 2. We have a second scenario where the arrival order is reversed. So thread 2 arrived first. It receives 0 as its the original value of the memory location and updated to 1. And then thread 1 come in, receive that 1 value as the original value, and then it would update the value to 2. So this is also a reasonable scenario where thread 1 will see an O value 1, thread 2 will see an O value 0, and memory location still reflects both the updates from thread 1 and thread 2. Timing scenario 3 is not as pleasant. We can have a situation where thread 1 read and modify, but before it has the chance to do the write, thread 2 came in and read the original to read that memory location. So both thread 1 and thread 2 will receive value 0 for the original value. And then thread 1 will write its result 1, but thread 2 will also write a result 1. So essentially thread 2 erased the update from thread 1. The update is purely based on the O value that did not incorporate the modification that thread 1 made. So this is a bad situation, and this could be a situation where 2 customers are reserving seats, and one of the first customer wanted to mark one of the seats as taken, and the other thread came in before that customer was able to update the map. The second customer grabbed the original C map and also try to reserve that same seat. So by the time the second customer came out, the second customer will mark the seat taken, but both of them will think that they got the seat, got the same that same seat, and that will cause that conflict during boarding process. Timing scenario 4 is similar, but the order is just a little bit reversed. So thread 2 did the read and modify, but before it has the chance to do the write, thread 1 came in and grabbed the O value, and then thread 1 will eventually write 1. And in this case, thread 0 and thread 1 and thread 2 both think that the O values were 0, and one of their updates is lost. In this case, it's thread 2's update. So the atomic operation is really designed to make sure that the entire read, modify, write sequence is performed only by one of the threads. And before that whole sequence complete, no other thread can come in and get an O value. So it guarantees that only 2 of the 4 scenarios can happen. Either thread 1 has all the read, modify, write sequence complete, and then thread 2 come in, or thread 2 has all the read, modify, write sequence complete before thread 1 can do any of the read, modify, write operation. So in this case, both updates will be reflected, and each one of the threads will receive the updated value from the other thread. So whether it's one before the other is okay, because we don't really care about the order. We just want to make sure that all the updates are properly reflected and no one's update gets lost. So this completes the lecture, and we don't have any recommended reading for this lecture. And once you understand the basic concept of atomic operations and race conditions and read, modify, write, we will be ready to go back to the histogram pattern and begin to craft a CUDA kernel that performs histogramming. Thank you.